So now we are going to look at the utility maximization problem, in short known as UMP. The consumer's problem of choosing the most preferred consumption bundle given positive prices and income can be stated as the following UMP. So maximize U of, okay, let's write U equal to U of x1 comma x2, okay, subject to the budget constant. So P1 x1 plus P2 x2 equal to M. Alright, now before we go to the Lagrangian, we should write a theorem, because that is very important. So, if P1 comma P2 strictly greater than 0 and U dot, there is the utility function, is continuous, then the UMP has a solution. This theorem we rarely mention it, so I mentioned it before going into the mathematics. Remember one thing, that the mathematics is famous and known to us, but apart from the 2 or 3 famous ones like Cobb-Douglas, CES, it doesn't really work. Even with quasi-linear, if it's an interior solution, this works. If it's a corner solution, then what the Lagrangian method helps us telling is that that the interior solution doesn't make sense, so you should move to a corner solution. So in that way, it may involve a lot of mathematics, but when we refer to different types of indifference curves, this setup has a very limited set of solution application. Now, apart from those places, when we have perfect substitute, concave, complement, what should we do? So we are going to write that first. Then we will move into the mathematics of it. So the optimal solution or any utility maximizing consumption bundle must satisfy the following, and based on these, what I am going to write, we are going to solve for the other ICs. Number 1, it has to be on the budget line. So that is why we do not really, in undergraduate, we do not always refer to the World Russian budget set. Number 2, the point must belong to the highest attainable IC. These 2 lines may seem trivial to you, but when in future classes we will work with substitutes and complements, you will see these 2 lines are quite helpful. The solution of UMP provides us Marshallian demand curve. Marshallian. So you should write demand function. Okay, so now let us go to the mathematics of it. There is a lot more to say on this topic, this method of Lagrangian multiplier, so to say, in Mathico, and you'll get to know even more if you look at one or other of the maths books. But for the time being, we will limit ourselves to the problem of UMP only, and the variations we will talk about them in a separate class in future of mathematical economics, where we will deal with quasi-concavity, quasi-convexity and other things. There we will talk about this at a more larger context. For the time being, the consumer is interested in maximizing his or her utility. Okay, so u of x1, x2, x1 comma x2, subject to p1 x1 plus p2 x2 equal to m. Let's put it 1. Consider the corresponding Lagrangian script L. This is so script L equal to u of x1 comma x2 plus lambda into m minus p1 x1 minus p2 x2, lambda strictly positive Lagrangian okay, we can write it. It's fine. Lagrangian proportionality constant. Okay, so now just to clarify, there is again this confusion. I've seen people asking this question, whether it will be a plus or minus and how will you write it. You can write it like this, or you can put a minus here and just write the opposite equation. There is no harm. In the end, you will get the same values. Alright. One important thing is that you should notice, which actually belongs to, so to say, Mathico. The point is that at optimum, you must understand that the value of this Lagrangian, this structure, is same as the utility. What I am trying to say is that the script L x1 star x2 star is equal to u of x1 star x2 star, because at optimum this budget will be exhausted, so this component will be 0. That is why it is so important that the consumer remains on the budget line, otherwise this will not happen, right? You cannot directly write it. So this is a very important observation here, because it helps to do a lot of things. Okay, and the biggest help is probably a simpler version of the Bordernesian determinant that we are going to write. Okay, right. So 3 variables, x1, x2 and lambda. Lambda takes the effect of, okay, let us spend a little time here. So the role of lambda, everybody knows, is the what it shows. Okay, we are going to derive that marginal utility of money thing. But in much simpler word, the thing is this: this is a constraint. So while you are maximizing utility, whenever you are, while consuming x1, whenever you are trying to increase the consumption of x2, it puts a boundary on how far you can go about the other commodity, and this boundary is given by this constraint. Now, because this boundary is here, obviously that has an effect on the utility achieved also. So that effect is measured by lambda. Okay. So the relevant first order conditions are 3 variables, 3 first orders. So del script del x1, you can write it like this also, which is equal to 0. And then del script del x2, equal to 0, and lastly lambda equal to 0. Okay. So what are they? So this implies del u del x1 or mu1 minus lambda p1 equal to 0. This implies del u del x2 minus lambda p2 equal to 0. And this implies simply your budget constraint. So lambda ensures that the constraint is satisfied. From these two, what we get is mu1 by mu2 is equal to lambda p1 by lambda p2, or it's simply p1 by p2. As lambda is non-zero, we have taken it to a positive. There is reason if lambda is negative, something very different will happen. Anyways, so what it reduces to is the famous first order condition MRS equal to P1 by P2. So this is the equilibrium condition of the, or for the consumer, actually for the consumer of this utility maximization problem, UMP. Now this holds only for interior solutions. For corner solution it changes, it's not equality so to say, and we will go to that, but not right now. We will go to that when we will be dealing with problems where you do have corner solution. This is the usual scenario, the famous condition as you know it. Okay. Now there is another way of arriving at it, and that is using the diagram. Okay. So MRS is basically the negative of the slope, and P1 by P2 is the negative of the slope of the budget line. And this is an interior solution. So this is your budget line, your fixed income. So this is one IC, this is another IC, this one. So you can have bundles of these 2 points, they are on the budget line, but the point is they don't satisfy the other condition that it has to be highest attainable IC. So how do you know it is highest attainable? Because it's a tangent. So this is my E, the equilibrium, and the consumer end up with x1 star, x2 star. So if we go diagrammatically, because this is going to be far more helpful with the non-standard scenarios. So at E, the equilibrium is attained where IC is tangent to the budget line. Remember, this is not an expenditure minimization problem. Here we have utility as the entity which can change, and the budget is something which is given. Okay, in EMP, that is expenditure minimization problem, is just the opposite. So there we have to draw a different diagram. I mean, similar but not identical. Okay, where IC is tangent to the budget line. So slope of IC, we go dx to dx1, and that will be minus MRS, and slope of budget line, again dx to dx1 minus P1 by P2, put them together, MRS equal to P1 by P2. Okay. So from this optimal condition, what do? We put the values of okay, let us write it here. So this equilibrium condition expresses x2 star in terms of, or x2 rather, in terms of x1. Putting this in script L lambda equal to 0, that is budget line, we obtain x1 star, x2 star, the optimal bundle. Now, as we know, that satisfaction of the first order condition doesn't really guarantee that our point is indeed a maximum point. For that, we need the second order. So for the time being, since we are more interested in having these demands and not really the details of the mathematics that is involved here, I am just going to mention the second order condition. Okay, so I'm going to add it here. So the SOC of optimization is, so this is our border Hessian determinant, and okay, let's just write, so bordered Hessian, so 0, P1, P2, P1, P2, UXX, UXY, UYX, UYY. You know, there are several different versions of this, like putting lambdas here, or writing script L's here instead of this U's. Okay, script L, but it doesn't matter because end of the day they are all same, right? That is why I started with the fact that at optimum this U star and this script L star are same. And that is why we are going to write something here which is very important to understand this process evaluated at optimum. So this is, because I am evaluating it at optimum, I can write P1, P2 and this U, UXX, that is the utility function. Otherwise, it's not what it looks like. Okay, it's something more general. Because this is an UMP, we can write it here. Okay, so what is the condition? The second order condition is that this one is positive. There is another condition also, and that is this part, which is this part must be negative, but in books or in your classes, I think people don't say that all the time. We just simply state the border Hessian of maximization problem, UMP should be positive, and we end it here, but that's not true. This is obviously the condition. With that, we have also this condition, we will write it as H1, which is that this determinant has to be okay. Let us check what is the value first. Okay, let me tell you the condition. This determinant has to be negative, and if you evaluate it, then this is 0 minus, oh sorry, this is P1, yes, so P1 square, so that means minus P1 square. P1 is, I mean, it doesn't matter whether it is positive or negative, the square term, so positive, P1 square is positive, so minus P1 square is trivially negative. That is the reason that in everyday classes, teachers don't really mention that we need, the condition is that this one is negative and this one is positive, and if we have a bigger problem, negative and so on. Okay. So this is actually the general condition, but as I said, that's a part of math. For our UMP, we should remember that this must be positive. We don't need to check this because trivially this is negative. Remember, this is always evaluated at optimum, because at optimum these two things are same, and this equality lies at the very heart of this calculation. Okay, so in the next two classes, we are going to look at specific examples. First of all, Cobb-Douglas, which is the famous one, and we are going to work with the general version that we have taken in the earlier classes. And then we are going to look at a very interesting problem, which is quasi-linear, where depending on the income, as I said before, it can be an interior solution or it can be a cornered solution. And in that cornered solution, we are not going to have this equality. Okay? Thank you.